Even though image processing is a separate object, it is closely related to computer graphics. Images are useful objects in computer graphics, as we have seen from example of texture pane. The image handling feature of Java 2D will be introduced in this lecture. So Java 2D offers an image model that must improve the AWT model. Images can be loaded, processed, and saved through the support of Java API. A digital image is a raster representation of a 2D picture and is defined by an array of point values called pixels. So an image is defined by a pixel. Each pixel value represents the color, which is gray level, and other attributes of the corresponding point. Even though image processing is a separate specialized subject, it does have a close connection with computer graphics. Images are useful objects in graphic rendering, and the output of graphic rendering is typically also an image. Java 2D offers more powerful image processing than old AWT. We will see in the next slide three models for image processing. In AWT, an image is represented by the image class. AWT uses the push model for images. The data for the image is not necessarily available when the image is created. An object implementing the image producer interface is a producer, and an object implementing the image consumer is a consumer. A producer acts as the source of the image, and consumer receives the data from a producer. Between a producer and a consumer, there can also be a chain of filters that implement both image producer and image consumer. So a producer pushes the data to the consumer in an asynchronous fashion, and the consumer cannot request the data, so the data transfer process can be monitored by the image observer. This model is designed with the idea of loading image over a network. The push model is not very convenient in image processing. Due to this, Java 2D introduces a new immediate model. The new mod image class, which is a buffered image, is used to represent an image with an immediately available data store. A buffered image contains a raster and a color model. First, for the raster, which represents the pixel value in numerical form, and a color model which specifies the mapping between the numerical values in the raster and the actual color of the image. And third, more advanced, which is Java Advanced Image, is an optional package that offers more advanced and comprehensive image processing techniques. So the three models that is known is the AWT, which is a push model, the Java 2D, which is an immediate model, and GAI, which is the full model. Here is a typical image processing cycle. The source image is usually given as a file in one of many image file formats. An image object is created in Java object to represent an image. The external image file is to be read into the image object. So the image can be displayed on a screen or a printer, and then or the image is can be processed by image processing operators or techniques. So to have a new object image, so the result is another image object. The processed image can be also displayed on a screen or rewritten to an external image file. So here a Java 2D image processing program usually uses buffered image to represent images. A buffer image object can be created using one of its constructor. For example, the following statement creates a blank buffered image. Buffered image bi equal new buffered image, the length and the width which is 300 and 400, and the buffer image type is integer RGB. To draw a buffered image, first we need to obtain a graphic 2D. To obtain a graphic 2D, we construct graphic 2D G2, which is cat operator graphic 2D bi dot create graphics. With the graphic 2D object G2, we may perform all types of graphic rendering on buffered image, just like drawing on the screen. In G2 SDK version, prior to 1.5 standard Java 2D does not directly support loading of buffered image from external file or network source. To load an image from a file to an image object, we can use the old AW facilities. Um, for example, which is the toolkit. In the applet, instead of using the toolkit object, an image can be loaded from a network URL using the getImage URL method of the applet class. Here, as we can see, how to read an image. To read an image, we will use Image IO API that offers support for direct reading and writing of buffered image. So to read an image from a file, we can simply call the following statement, which is buffered image di image io.read file. And also to display an image, we can use the g2 draw image as 00 then on the graphic 2D. And the last parameter of the draw image is an image observer, because the class component implements image observer interface. The subclass can be used as generic parameter. We may also use null for the image observer if this code is in a graphical user interface component. Then a graphical user interface component such as a gPanel object is usually used as the image observer. The purpose of the image observer is to support asynchronous loading of image in the original AWT component. Here in the example, as we can see, is how we can read an image and also how we can draw an image. We read an image from a file and put it in IMG, and then we use the draw image on the graphic to draw the image, and here is the output of this code. The operators in the once we have buffered the image using the buffered image object, we may apply image processing operations to it. Just 2D contains a set of classes for image operations. The classes implement the buffered image op interface as follows. A buffered image op contains rescale op, lookup op, convolve op, color convert op, and affine transform op. The first operator, which is the rescale op. The rescale op performs pixel by pixel rescaling of the pixel values by a linear function. A pixel value is multiplied by a scaling factor and then an offset is added. If which means multiplied by scaling factor A and then adding an offset B. If f of x y is the pixels of the initial image and g of xy is the image is the processed image, then the rescale operation can be written as follows. G of xy, which is the processed image, equal to A, which is the scaling factor, multiplied by f of xy, which is the color of the initial image, and then adding the offset. Then G of xy will be the color of the a new color of the same position xy. For example, if we take A equal to -1 and B equal to 55, and we will try to convert the color f of xy, which is 0, to find the color g of xy. Then we multiplied -1 by 0 and add to 55, which is equal to 255. Then g of xy equal to 255, which means if it is a dark color, it will be a white color. And also, if we take, for example, f of xy equal 2, then we multiplied -1 by 2, which means -2 plus 255, which will be 253. Then a dark gray will be converted to light gray at the same position xy. To write the code of the rescale op, first we read an image from a file, and we put it in img, and then we create the rescale op by putting the scaling factor -1.0 and the offset to 255, and then we call the function filter in the op object op.filter of image, and then the new image will object image, which will be I. Then we can draw I. As we can see here, the image is inverted, where the dark colors will be light colors and vice versa. The second operation, which is the color convert op, which perform also pixel by pixel conversion of colors. The operation can be specified with colored space. So first we read an image from a file, and then we choose a color space cs, which is color space dot get instance of color space of gray color. Here we will try to change the image from colored image to grayscale image. Then we create the color convert op, which is new colored convert op of cs, which is the grayscale image, and then we apply the filter on the image to create a new image I. And here is the initial image before applying the filter, and here is the converted image after applying the filter. Then the image is converted from colored image to grayscale image. The third operator, which is the lookup op, which performs pixel by pixel conversions of pixel values based on lookup table. The operator can be expressed as you can see here, we make a transformation of the color to the color to get the new color in the new image. To apply such a conversion to the source image, we must create a lookup table that associates all the values in 8-bit range to their complements. 8 bits, which means 2 power 8 from 2, which is 256, then from 0 to 255. First, we create an array of shorts of 256 colors, and then we make a transformation. We create an array, then we try to fill the array by the following equation, which is data of I equals 255 minus I. Then the first value is 255 minus 0, then 255 minus 1 is 254, etc. Then we create the lookup table based on the data of the array. Then we try to apply the filter, which is the op on the source image to see the destination, or to get the destination image. The affine transform perform affine transform on the image. The operator does not change the value at the previous operators. Instead, it moves the pixel to a different location. First, in the previous operations, we make the function or the transform on the color, which is on f of x. Now we will make the transform on xy to get g of xy. Then the same color of the pixel, but we change the position of the pixel. The affine transform object is used to set the transform. The formula is given by. So we create an affine transform, and then we make the rotation on this affine transform. And after that, we can apply it on the initial image, and then initial image to get the following transform shape. The convolve op define convolution operators. A convolution is a linear transformation. So if an image is represented mathematically by a function f of xy, the convolution of the continuous function can be represented by g of xy, which is a double integral of the kernel, which is the filter, multiplied by the function du to d. Here is in the case of continuous function, where k is a fixed known as a kernel, and the property of convolution is determined by this kernel. So by choosing the appropriate kernel, we may achieve various effects on the image, such as smoothing, sharpening, and edge detection. So for digital image, the integral will become as summation. So double integral will become as double summation, where I goes along the entire image, the rows of the entire image, and j go along the columns of the entire image. At each point, only the 9 pixels around the point need to be considered for calculation. So the kernel is at most of the cases 3 by 3 filter, a matrix filter, and f of xy is the image. So if we want to study or to calculate the value at a specified point f of ij, then we multiply f of ij by the center of the pixel and the neighbors of f of ij by the neighbors of the pixel, and then make a summation to calculate the result in the processed image. Here is the first kind of filter or kernel, which is the smoothing kernel. The smoothing kernel is defined by 3 by 3 matrix, which is equal to 1 over 9. The smoothing kernel, so if we have 2 pixels in the original image that has different color, for example, pixel has a value 0 and the other pixel has a value 1, then the smoothing filter try to increase the value of 0 and decrease the value of 1, so that the 2 pixels near each other will be approximately the same. So to define the kernel, we will use an array of 9 values, and then we set these values into 1 over 9. As we can see here, for int I equals 0, then we set the the data of I equal 1 over 9, and then we create the kernel by decomposing the data into 3 by 3 square matrix, and then we create a convolve of by using this kernel and applying it to the initial image. The smoothing filter is used to remove voice from an image, but also if we use a high level of smoothing filter, the image may be converted to a blurred image. Here is the original image, and here is the smoothing image. So the kernel is defined by 1 over 9. Here is a sharpening filter. The sharpening filter which contains the second order derivative. So the initial image will be sharp, and then we get the processed image. The array of the sharp filter or kernel will be 0, minus 1, 0, minus 1, 5, minus 1, 0, minus 1, 0. And then we can create as before the kernel of the image by using a new kernel 3 which is a square kernel, and we take as an input the one-dimensional array, and then we create the convolve of which is an op, and then we can apply the filtering to the initial image to get the filtered image. So as we can see, the filtered image will be sharp more than the initial image. The next filter, which is that make the edge detection, which make the first derivative. As we know, as a definition for a derivative, it make a difference between two consecutive pixels. So the large values only will appear, which means the edges and the corners of the image. The filter, first we will define a one-dimensional array as before for the first order derivative, which is 0, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 0, and then we create the kernel, the 3 by 3 kernel, and we apply. As we can see here, here is the original image, and here is the filtered image, and also the filtered image shows also only the differences, which means this point is different color of its neighbor, so it we will see the edges only. So several operations are implemented to perform common image processing tasks, including smooth, sharpen, edge detection, rescale, rotation, and grayscale. So as we see before, the smoothing operation is the convolution defined by the following 3 by 3 kernel, where all its value is 1 over 9. So using this, it will make the average of a pixel. The sharpening operator is defined by the following kernel, which is 0, minus 1, 0, minus 1, 5, minus 1, and 0, minus 1, 0. The edge detection operator also is defined by 0, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 0. The rescale op uses the rescale op class. It is designed to brighten the image. The rotation operation uses the affine transform op class. A rotation of pi by 6, as we see before, is defined by an affine transform and applied to affine transform object. The grayscale operation uses the color convolve op class to convert the source image to grayscale image.